Okay, so let us now get into some math. There will be math, but in this course, but it will not be very complicated math. So, and I'll go through slowly and in detail, step by step, if there's anything involving math. Okay. All right. So, how to get the degree, compute the degree of a node using the adjacency list or matrix. It's just the size of this linked list, right? So the number of neighbors for a node is the degree for a node, so you can compute it. Similarly, in the adjacency matrix, for each row, sum up the ones that are out there, and that's the number of neighbors. Okay. Now, similarly, for undirected graph, we just say degree for a node. Whereas for a directed graph, we have what is called an incoming degree and outgoing degree for a node. So for node 1, it has two outgoing edges, so its outgoing degree is 2, and it has one incoming edge, so its incoming degree is 1. Node 5 has two outgoing edges, so its outgoing degree is 2. It has no incoming edges, so its in degree is 0. So in the case of directed graphs, each node can have an in degree as well as an out degree. So the out degree represents the number of outgoing edges from that node, and in degree represents the number of incoming edges to that node. So node 2 has two incoming edges, so its in degree is 2, whereas it has no outgoing edges, so its out degree is 0. So for undirected graph, we don't have incoming or outgoing, so basically call things as a degree, and that's just the number of neighbors for a node. So now a very interesting relationship is there between the number of links or edges in a graph and the node degrees. Okay, so again, if I ask you a problem, given an undirected graph like this, how many edges are out there, right? So right now, your only approach would be to manually count the number of edges, 1, 2, 3, 4, 5, 6, and you'll say there are 6 edges in this graph. Okay, so, but think about a very large network like 1 million, network involving 1 million nodes that may have several millions of edges too. So you really cannot count, right? Even if you're given visually, you cannot really count the edges and say this is the number of edges. So what we'll see is there's a very good relation between the degree of the vertices and the number of edges in the graph. So the idea is this. So given a graph, based on the number of neighbors, you get the degree of a vertex or a node, right? So you just sum up the degrees of the vertices, sum the degrees of all the vertices, and divide that sum by 2. And that's this formula. So for I equals 1 to n, I is the node ID index, ki represents the degree of node I. So sum the degrees of all the nodes and divide that sum by 2, and that will get you the number of links in the graph. Now you may wonder, why is this true? Okay, so let's go back to that example here. So when you count the degrees of the vertices, right? So when for node 1, its degree is 3. For node 2, its degree is 2. So it's like, let me put it here. Let me open a different Word document. Since we don't have a board to explain in class, we'll use a Word document. Okay, so let me write the node and the degree. So 2, 3, 4, 5, and the degree is 3 for node 1. For node 2, its degree is 2. For node 3, it's 2. For node 4, it's 3. For 5, it's 2. So when I say 3 plus 2 plus 2 plus 3 plus 2, so that's the sum of the node degrees, right? So this 3 corresponding to node 1 considers these 3 edges, the edges between 1 and 3, 1 and 4, and 1 and 5. Now we notice this 2 corresponding to node 3 also considers these edges 1, 3 or 3, 1, however you want to call it, and 3, 4. So it means each edge is being considered twice when you do the summation, right? So it is considered twice in the sense that it's considered once for each of the end vertices. So there's a terminology called end vertex. There's nothing but for an edge, the vertices at the end of the two edges are called the end vertices. So for this edge 1, 3, 1 and 3 are the end vertices. So for edge 1, 4, 1 and 4 are the end vertices. So when you sum up the degrees of the vertices, you are considering each edge twice, once for each end vertex. So that's why if you divide the sum of the degrees by 2, that will get you the number of edges or links in the graph, because each edge is considered twice when you sum up the degrees, and you divide that sum by 2 and you will get the number of edges that you counted. So that's the idea behind this formula. Okay, any question on this so far? Okay, so let us continue. So now you could also have another interesting relation involving the average degree of the nodes and the number of links and nodes in the graph. Okay, so according to this formula, let me type it out here, that's more easy to visualize. So what we have right now proved is this. So the number of links in the graph is 1/2 of the sum of the node degrees, equals 1 to n. So n is the number of nodes and ki is the degree of node I. So this is what we kind of proved, or kind of got ourselves convinced that there's a relation between the sum of the node degrees and the number of links in the graph. Now if you can simplify this expression, or kind of rearrange this expression and say so what we can say about this from this expression also is do a kind of what's called cross multiplication. So this 2 goes onto the left hand side, so the sum of the node degrees is 2 times the number of links, right, just because of cross multiplication. So now in statistics we can compute average through different ways, and one common way is just sum up the numbers, then divide by the number of numbers you summed up, right? So if you want to compute the average degree of the vertices in a graph, you could indicate that with a symbol like this to tell that's the average degree. Sometimes we also say k bar, put a k and a bar and a line on the top of the k, so that's also a way to represent the average degree, but we'll use this symbol. So if you want to average the degrees of the vertices, you can do what? Sum all the degrees and divide that sum by the number of nodes, right? So we can say the average degree of the vertices in the graph is the sum of the node degrees, how many nodes are there, sum the node degrees divided by n, the number of vertices. So this is one way to compute the average degree, isn't it? Now what you can do is combine these two expressions. So the sum of the node degrees is a common term in both these expressions. So based on our first analysis, we said the sum of the node degrees is twice the number of links. Based on the second analysis, or just by definition of average degree, it is the sum of node degrees divided by the number of vertices. So now instead of the sum of node degrees, we can put 2 times the number of edges, and that will give a very good expression for the average degree. So that is going to be like 2 times L. So the average degree of the vertices in a graph is 2 times the number of links by the number of vertices. Now you see something is very interesting with this expression here. If I want to know the average degree of the vertices in a graph, I don't really need to give you the actual graph. You don't really need to be given the actual graph like this. All I can say is, if I tell you the number of edges and the number of vertices in the graph, you can tell me the average degree of the graph. So for example, this graph has what, 1 2 3 4 6 edges and 5 vertices. So I can do the math. 2 times the number of edges is 6, divided by 5 the number of vertices, 2.4. That's the average degree of the vertices in the graph. So you see, I did not even compute my degrees and sum them up. I don't even need to know the graph. As long as I know the number of links and nodes, and I should know it's an undirected or directed graph. So those are things I need to know. It's an undirected graph with 6 links and 5 vertices. As long as I know this information, I can come to the average degree of the graph. I don't need to physically look at the graph. Okay, and you can cross check. You computed just now the average degrees or the degrees or the vertices. So vertices and degrees like this. You can sum these numbers. 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 3 is 10, 10 plus 2 is 12, divided by 5 vertices. So 12 divided by 5 is also 2.4. So the average degree should tally in both ways, based on the number of links and nodes, and as well as based on the node degrees. Now you may wonder, can we do a similar analysis for directed graphs? Yes. Again, but the directed graphs has incoming edges and outgoing edges, right? So if you look at this, the sum of the degrees of the incoming neighbors is going to be simply the number of links or edges you have in the graph, because you see in the undirected graph, when you sum the degrees, you are counting each edge twice, basically in each direction. So when you consider the degree of 1, you are considering the kind of outgoing part from 1 to 5, and when you consider the degree of 5, you are consider the outgoing part from 5 to 1. So that's what internally is happening. So each edge is captured twice. Whereas here, when you sum the incoming degrees of the vertices or sum the outgoing degrees of the vertices, each edge is considered only once. So for example, if you want to calculate the sum of the out degrees of the vertices in this directed graph, for node 1 it is like 2 outgoing neighbors, nodes 2 and 3 doesn't have any outgoing neighbors. For nodes 4 and 5, we have 2 outgoing neighbors. So if you sum the out degrees of the vertices, so the out degree of vertex 1 is 2, for 2 and 3 it's 0, for 4 and 5 it's 2 each. So the sum of the out degrees of the vertices is 6, and that's the number of links in this graph. Okay, same thing you can get by summing the in degrees of the vertices, that will get you the number of links or edges in the graph. So that's why I have this relationship. The number of links in the graph is sum of all the incoming in degrees of the nodes, and is also equal to the sum of all the out degrees of the nodes. And from this we can also get the relationship involving a degree. So you can say the average in degree as well as average out degree. So let me put it here to avoid the confusion. So the average in degree for a directed graph is sum of all the incoming neighbors, the degree, the in degree, sum of all the in degrees divided by n, the number of vertices. That is the average in degree for a directed network. You can get the average out degree for a directed network by summing up the number of outgoing edges and dividing that sum by n. Now how can we relate the two? You see, the sum of the incoming degrees is same as the sum of the outgoing degrees, and that gives the number of links. So put that expression here. So sum of the outgoing neighbors is equal to the number of links. So we can mention that here and replace the sum with the number of links and divide that by number of vertices. That's going to be equal to the average in degree. So previously, for the average degree for undirected graph, we had 2 times the number of links divided by the number of vertices. Whereas for directed graph, the average in degree is just simply the number of links by the number of vertices. And the same definition will also hold good for the average out degree of the vertices. Okay. So that's the kind of difference between the directed and undirected graph with respect to the degree and the relationship with the number of links and vertices. So we'll do one small thing before we stop for the break. So as I just said, again, so even in the directed graph, you don't need to be given the actual directed graph. As long as I tell you these are the number of directed edges and this is the number of nodes, you can calculate the average in degree or average out degree for the graph. So that's why in this table, I have just listed whether the graph, so these are all the real world, some of the examples of the real world network graphs. So for each graph, I have listed what entities constitute a node and what constitutes a link between two nodes. But what we need to focus is on whether it's a directed, undirected, and how many nodes and how many links that does the graph have. So using these three information, we can compute the average degree of the vertices. Okay, so we don't need to be really given the actual real world network. So this graph, say for example, the yeast protein interaction network is untitled graph of 2018 vertices and 2930 edges or links. Since it's undirected, the formula for the average degree is 2 times the number of links divided by the number of vertices or nodes. So that's going to be 2 times the number of links, which is 2930, divided by the number of nodes, which is 2018, and that will get you the average degree. Whereas for the E. coli metabolism network is the data graph involving 1039 nodes and 5802 edge links, and this is a directed graph. So the average, say in degree, so even though I did not represent here, we are really calculating average in degree or average out degree. Okay, so this degree is meant for the undirected graphs, but since we also have directed graphs here, we have to say this is the average in degree or the average out degree. So divide the number of links by the number of nodes, that will get to the average in degree as well as the average out degree. Okay. So this could be a small problem in an exam. I could give you just these numbers and whether the graph is directed or undirected, and you should be able to find the average degree of the vertices. Okay. So let me stop and